Okay, good morning, everyone. My name is Brett Nicholson. I am one of the Intelligent Sensing Group's marketing managers for the Americas. And today we're going to talk about Vision IoT. Before we do that, first start off, I just want to see a quick show of hands. Pavan talked about the wide adoption of imaging sensors as another sensor technology over the recent years. How many of you in the room are currently using an image sensor in your products and or are investigating or potentially planning on using an image sensor? Okay, good portion of you. Great. So hopefully you'll find this the next bit of information, or for those who did not raise your hand, maybe you'll start thinking about how potentially a image sensor or an image sensor sensing solution or an intelligent sensing solution using radar or LiDAR might be able to solve some of your customers' problems. So today's talk, I'm going to talk about, start with talking about kind of a theme that Pavan mentioned, balancing performance and low power and what's driving this lower power consumption. Then we're going to go on to requirements for Vision IoT, because those requirements, we need to think of them in two different ways, from a human perspective, but also a machine perspective. They can be, they do share some similarities, but there are some key differences. So, and then we'll continue on with energy efficient imaging solutions for battery powered applications. As Pavan mentioned, there's a tremendous growth in this, and we're going to be talking about edge devices, and these devices and being able to be battery powered are a key component of that. Then I'm going to talk a little bit about some of the imaging technology enhancements going on right now and available through ON Semiconductor and various ON Semiconductor solutions, such as low light, HDR, or high dynamic range, AI, and also near infrared plus, which is being able to improve the sensor's ability to convert near IR photons into usable electrons. And that helps you improve your image quality under lower light conditions. Then moving on to, we're going to talk a little bit about robotics and some of the solutions that are available, and talk about some of the demonstrations that you'll see next door. And then to help make your lives easier, I'm going to talk about some of the tools and partner ecosystems that might be of interest to yourself. So with that, let's talk about, Pavan talked about these edge devices becoming more intelligent. What you see here is kind of a diagram, or kind of a vision for, as you see the cloud centers, thousands of units up here, cloud services, and aggregating and from the fog or the nodes, taking all that data in. But as that more and more data starts moving up into the cloud, there's more and more pressure to do more processing down here at the edge or the bottom where all these sensors are located. And so that means those devices on the edge, there's huge growth opportunities for all sorts of different applications and market segments and technology modalities. Also, there's a drive, because of those devices, they're going to be increasing pressure to move that to lower power and increasing that performance. So, with that, also another dynamic is this getting away from wires. Everything is becoming increasingly wire-free, from wireless charging on our cell phone devices to, as you see there, doorbells or robots or vacuum cleaners now are all becoming more and more robotic, to door locks, speakers, assistants, etc., to smart meters. So those are a few of the examples also that we're seeing driving this wireless or wire-free Internet of Things devices and smarter devices. Okay. While we see these trends, there's also still a division within that within the power and the battery operation. On the left-hand side, you see an example of kind of this processing intensive environment or applications and products where you do require that large power source and or larger power capabilities, like in larger robotics, versus the right-hand side, which becomes power and becomes very critical and a driver as well as cost. Well, we can't kid ourselves, as cost is a key driver in many of these smart or edge devices going forward, such as we talked about, battery cameras or doorbells. So, but we still see that. And so you might even think of it as, on the left-hand side, more commercial or industrial, and then power critical, more geared towards those consumer or larger volume applications like smart retailing. Okay. I talked about this thinking of imaging sensors, and you have to think of them in kind of two different ways and kind of the requirements for that. On the left-hand side, you see kind of imaging viewed by humans. So smart cameras, security cameras, CCTVs, et cetera, where you've got a human that's actually looking at the camera output and then doing their own analytics on those images. Well, on the machine vision side, you actually have a machine doing that work. And so as a result, you're going to see differences. The machine's going to look at things a little differently and want to see that image differently than a human, and in order to have those algorithms work effectively and efficiently. So, and then you see kind of the emergence there in these smart systems in a doorbell camera, where you're going to see both sides, right? The smart doorbell cams in this example, the future will both incorporate AI or algorithms to, say, wake up or come out of a sleep mode, to turn on and go to maybe a high resolution video frame rate to film like a scene, someone coming up to the porch or invading that field of view, and then but still use it effectively for a human, where you can then log into your app and say, hey, that's just Amazon making a delivery to my house. It's okay, that sort of thing. And then once the machine vision portion senses that Amazon delivery driver going away, then the machine can go back to maybe a lower power rate or a lower frame rate. Okay. So that's kind of one examples of that kind of emergence of the way of doing things. And you got to think about that depending on your application. Okay. To get more specific in that, what you see on the left-hand side is kind of specific needs. On the imaging or the human side of things is really about color and image fidelity. As I said, you're viewing the image from a human perspective. What can you make out and do your own analytics on it? A machine's going to look for moving objects, as I mentioned, the doorbell camera, security camera, looking for that movement going on, and then being able to take an image or use an image that of that movement and still be clear enough and not have what you see in the image here is motion blur. So, and I'll talk a little bit more about that later in motion blur and how that impacts things. But they still have common things, right? In both situations, the human and the machine is dealing with varying light conditions. And so how do you deal with that? Shadows. If you take once again, that same example, the doorbell cam, sometime you're going to have bright sunlight. Other times it's going to be fairly dark or in a shadow. How do you deal with that? How do you deal with a wide field of view and then do a close-up field of view if you want to do, say, ID recognition? Do you want to be able to see the person's badge and verify that it's that the delivery is FedEx or it's some other service provider coming to your home in the case of like an electronic door site thing, so you can look in the door and see, hey, that is the heating and repair guy, and identification verification. So, and of course, in both cases, cost becomes a player. Okay, so we also want to talk about, just to get some other ideas for those of you, depending on what markets you're individually play. I've already talked about quite a bit about doorbells. AR, VR, of course, there's a lot of talk about that, but there's others at barcode scanning. Barcode scanning increasingly is becoming broader. It's not just for grocery stores and package delivery systems anymore. You're seeing it more and more, of course, at the airports, but more and more companies are using barcode for inventory management, that sort of thing, and smart, industrial and operational situations. So, of course, wearables and IP cameras. I'll talk about trail cameras. Trail cameras, wildlife cameras is another area that we do see a lot of interest in this sort of technology and adoption. Okay. I alluded to one of the key things. We talked about this theme of reducing power. And what this slide is showing is we're incorporating at onsemi a lot of becoming smarter in our actual image sensor designs. And that means putting in features that you see kind of here of, in this particular example, it's our ARO 430. It's a 4 megapixel, 1/3 inch sensor. But one of the unique features of it is the ability to, when you're operating you can operate the device up to 120 frames per second if you need to, if there's motion or something of interest. And that is at full resolution, and your power consumption is 230 milliwatts. But if there's no activity going on, you can link the sensor to some kind of motion a sensor there, and it can wake up or go to sleep after that motion is gone and go to sleep, and then you reduce your power consumption and only operate the device at about 1 frame per second. So this is kind of going back to that doorbell or a wildlife camera or other situations, or even security cameras, right? You can go to sleep, use low power, help you on the battery side of things, and then wake it up as needed. So that's another key feature. And of course, there's other techniques. The other one is using some clocking features or different operation modes. So I wanted to talk about that. That's some of the things that to look for in some of our image sensor solutions. Okay. I kind of alluded to some of them. I just want to kind of put some ideas in your head today. I talked about motion detection sensors, incorporating them into your devices. Someone walks in a room, other PIR technologies. You can also do some speed adjustment on the operation or your camera design of things. Also, you might think about doing pulsed LED illumination. So you don't have the near IR particular or other LED illumination constantly on. You can use pulsed and then sync it up with your motion detector to help drive that lower power consumption overall into your system solution. Okay. The another opportunity there you might want to look at is your SoCs or the other back end. What happens further on down the chain with your image sensor data, your ISP and your SoC or your other processors there, other opportunities to reduce your power consumption overall to the system. And that's something that onsemi and our FAE teams as well as our distribution partner teams can help you. We do have a lot of existing block diagrams and reference designs that can on similar technologies to help you optimize that and take a look at schematics. So. Okay. If we talk about the benefits, of course, Pavan talked about lower power, of course, lower heat. That improves reliability. But also for an imaging sensor, reducing the heat means reducing dark current. And for dark current, the lower the dark current, that helps improve your signal to noise, and that, of course, improves your image quality overall. And so that's another key feature you want to think about is on that side of things on the dark current specification. Okay, one example I show here is this the ARO 430 that I mentioned earlier. This kind of gives you a snapshot of this particular sensor. It's got great full well that, for those of you that are not familiar, full well kind of refers to, in simple terms, the size of the pixel bucket, the ability, how many electrons can that pixel collect. You see here once again the chart. You go from 120 frames down to 1 frame in ultra low power mode, scalability. And this particular chip, the 430, also has a sister chip, the ARO 431, and that improves the 431, adds some additional what we call near IR plus technology, and I'll talk a little bit more about that later on. But that bottom line is that's for applications where you are at a day or a low light. If you are dealing with kind of daytime imaging and you can't control your light levels, then it gets dark and you want to improve your image quality under those low light conditions. Okay. Another device that we think about for artificial intelligence that was developed is our ARX3A0. It is a small relatively small 1/10 inch optical format. It's 560 by 560 pixels using a 2.2 micron BSI pixel or backside illuminated. And we're seeing, it was originally developed for the AI market, where in a lot of these applications, fingerprint, iris identification, and some of you may say, oh, it's 560 by 560, that's a very high resolution. But at the end of the day, there's many applications that don't require high resolution. And that's really the point of this sensor. This is what we call an ultra-fast rolling shutter device that allows us to use a BSI more sensitive pixel, improves the near IR sensitivity out at 850 and 940, which are the most common near IR LED wavelengths. And so, and it's a device that also can run at 360 frames per second. So you can, for most situations, people tracking or something like that, or watching a device, it's not 360 frames per second is generally going to be sufficient to capture that motion and not have that image blur that you may have seen on that fan slide. So so this device, and it's relatively cheap. It also relatively inexpensive, I should say, and might be a solution for many applications. The other nice thing about this device, and you'll be able to see it in the demo room, is that it is available in what we call a module solution. So for many customers, including maybe several of you in the room, you don't want to deal with a raw image sensor trying to come up with and do a camera design. You may just want to say, hey, I just want an image sensor with an integrated lens with a certain focal length and field of view. And therefore, I want to be able to put it onto my board and then link it up to a Jetson or some other coprocessor or a Xilinx solution or an Altera, depending on your preference, and then be able to get, as I say, a pretty picture out. I just need a pretty picture. I don't want to go back and do all this engineering work. I need to get my product to market. That's not my core expertise. Well, then ON Semiconductor does offer and is starting to offer more and more of our imaging sensor solutions in these little modules. So I encourage you to stop in next door and come by the booth this morning, or talk to Avnet and Future and Aero, our partners, about those potential solutions, because that may be an opportunity, and this particular sensor is available as in a module solution. Okay. And on with that, there's actually a live demo showing this, and this particular slide shows a kind of a high-level block diagram of from ON Semiconductor, where we worked with a customer. You take an ARX3A0 that you just saw on the previous slide, link it up with some battery management. We leveraged a SunPlus image sensor processor and linked up some memory, and then linked it up with some ON Semiconductor RSL10 Bluetooth technology. And so the demo next door is showing this small low energy camera, and then using this Bluetooth technology, transmitting still images over Bluetooth to a cell phone. So if that's something of interest, I definitely encourage you to take a look at that. But it also shows here, as I mentioned earlier, the ON Semi team and our FAE teams have a fairly significant library, and it can help you out on your block diagrams and working through some of these designs, and hopefully save you a lot of time and energy. Okay. I've talked quite a bit about battery-powered devices and cameras, but we're also seeing more and more interest, and you will see in the marketplace more and more use of imaging sensors in non-battery operated devices or in smart appliances, where we're seeing it. And this is not only in the consumer side of things, but also in the industrial commercial marketplace. The first one that jumps out is refrigerators. You may have seen some of the early refrigerators, some of the advertisements already talking about image sensors and putting image sensors in the refrigerator to say you can log in and look at your fridge and say, oh, okay, do I still have milk or vegetables in there, that sort of thing. But also we're seeing them in coffee makers, and you say, well, why would you put an image sensor in a coffee maker? Any ideas? None? Okay, it's kind of the same reason. I'll give you another hint. In the industrial world, they're talking about using image sensors in sanitizer dispensers or soap dispensers. Any idea? No? They're There's part empty. You can use other technologies that are a little cheaper, but you're using it for authentication of the refills that are going into the machine. So in other words, if you're Keurig, you're putting an image sensor in there to make sure that the consumer is actually using a Keurig authorized pod into the machine. Or in the case of hand sanitizers and hand soap, if you're in a hospital, one of the key things there is to make sure that they're using hand sanitizer that is been tested and authenticated to kill, the 99.9 health requirements of the germs in there. So part of the job is that the soap dispenser guys, so I want to make sure that the hospital purchasing person doesn't go off and buy some cheap sanitizer that we find out later that doesn't kill anything. And so they're trying to use and get ahead of that and putting image sensors in those soap dispensers so it can read a little barcode. And the barcode, a proprietary little barcode, and say, yep, that is definitely XYZ companies. That's my soap going in there. So therefore, I have assurances that, the hospital is using a decent sanitizer or a soap or that sort of thing. And it comes back to that. So they're just, once again, throwing ideas out there that some of our customers are starting to incorporate and think about image sensors. And of course, the robotic vacuums, robotic lawnmowers, we're seeing more and more of that interest of saying, hey, I need some image sensors. I got my vacuum, and now I don't have to, if I can get a robot to mow my lawn on the weekends, that's one less thing I have to do, or get my riding lawnmower to be robotic. Then I can sit back and watch the football game as I'm outside actually riding the lawnmower around. So those types of things you're starting to see more and more. Oh, yep. It depends. To be honest, we have, when you say 1K pricing, depends on the actual sensor. So the small little ARX, a little imaging module, you should be able to pick, in that sub $10 range. So we have sensors that'll go from $1 all the way up to $10,000. Within the portfolio. And I'm being all honest and so on. But there's, and that's where we didn't talk about it, but it comes into cost typically relates to the optical format. Optical format is roughly the size of the sensor. The bigger the sensor, the less die per wafer, and then the more, the higher cost, right? So that comes into play. And so now, having said that, is you have to balance that with your application. And so one of the things I didn't talk about is resolution. You may, that ARX 380, I mentioned, the low, that may be good. And this, I get this all the time as I get, for example, customer comes in and says, I need 4K resolution for a body cam. And it has to be really good at low light. And it has to be super cheap. So, they'll say, okay, so 4K, you want 12 megapixels if I meet that requirement, but then it has to be cheap, so it has to be really small optical format, which means the pixels are really small, and the pixels are really small, so that means you're really limiting your dynamic range. And so that, and in order to get your costs down. So there's also these trade-offs, right? And so that would be another key message if you don't pick up today, is make sure you balance it. You may find a 2 megapixel sensor with a 1/3 or a 1/4 gives you a better image quality from a human perspective if a human's using it than something else like a 4K. But oftentimes customers get caught up or get sucked into the marketing side of things and go, I have to have 4K. And so once again, and we have eval kits. You'll see some of the eval kits. I encourage you to play around with that with a 1 meg or a 2 meg. I have the same questions. What sensor do you recommend for a digital door, the eye camera? I can't think of the eyesight that you look through to secure. And I'm like, well, it depends on what you want to do, because you're going to need dynamic range. You're going to have certain length, right, that you want to focus on, but you also want to be able to tell whether that, read the person's badge or that sort of stuff. So I definitely encourage you to leverage our evaluation kits and look at various sensors, because you may have a 1 megapixel sensor that's $8, or a 2 megapixel that's $8 and a 1 meg that's $15. So it just depends on the particular features and frame rates and all that stuff. So good question. Thank you. All right, so another thing I kind of touched upon is on the imaging, we're going to transition towards imaging technologies. And one of the things that comes into play for many applications is high dynamic range or dynamic range rendering. And what you're seeing here, for those that maybe are not that familiar with it, but we're showing here different scenes, and dynamic range just refers to the difference between the lights and the darks in the scene. So if you see here a 20 dB scene, you have a very consistent, the light is probably controlled as you're looking at this painting. Now you're outdoors, it's pretty overall bright, there's not a lot of shadows, and then you're seeing the dB go up. Here you're seeing an indoor scene, you still got lighting here, but you've got lots of shadows around the couch, etc. And then you start going in outdoors. This is an 80 dB scene example. And depending on your application and depending on how your end customer is going to be using the device. So if you're thinking about security cameras, so right, you see the security cameras, you may be offering a security camera system and you think the customer is going to put them all outside the house. Well, why wouldn't they put one inside the garage door and look at the garage and be able to look inside the garage door or in the stairwell? And then that way, all their security cameras inside and outside of the house. So that's where you've got these different lighting environments become particularly important, and become particularly important when you're looking at and evaluating image sensor solutions. So with that, we talked about some of the two key things, or two different modes that come into play, or modes or techniques that we can use with the image sensor is, and you want to be able to have that dynamic range without motion artifacts. So if you got something moving, and so one of the techniques is this is an example here of linear mode or a standard dynamic range, but we can do what we call an HDR mode, where we take two images in slightly different in time, one long exposure, one short exposure, and then we can, the ISP, typically it's an ISP for these devices, or like an SoC solution from one of our partners, such as Ambarella or Fuhan, or any one of those ISP providers can then recombine those two images into one image, into this image that you see down here. And it's actually, I'll be honest, the clarity, once again, going back to the human perception, fidelity, this is a great example. The image here that you see is like, oh, that's okay, but it's actually much better on my monitor because of the fidelity through the projector. It loses quite a bit. So once again, if you are looking at things from a human perspective, make sure you use good monitors and good displays, and understand that too, what your customer going to be using. So here's an example of another 2 megapixel device, HDR capabilities. Going back to the gentleman's question earlier, this is a 2 meg. This is using a 3 micron pixel. It also has dual gain conversion, which is another technique. I talked about technologies that we incorporate on the sensor to help and improve the overall image quality, and improve the HDR performance of the actual in the sensor side of things. And then this particular device also, I talked about this near IR enhanced sensitivity as well, to improve the night vision or low light vision. Okay. Once again, building on that block diagram, here shows a block diagram of a 1080p that we worked with one of our customers. This was built around an ARO 237. This is a 2 megapixel, 1/3 inch format sensor, linking up with an Ambarella S5L, 33M, etc. You got it linking up with an ambient light, IR LED drivers, power management side of things, microphones, speakers, etc. So those are all we actually have, this is just kind of a top level block diagram, but we've got, we can break into the actual the components and BOMs and everything else for you. There is a demo next door from one of our customers called Pinnacle Imaging. That particular demo is using our ARO 239. And I talked about on the previous slide, 2 exposure HDR. Well, the Pinnacle system is actually leveraging the 239 29, which allows you, once again, has newer technology. It allows you to do 3 exposure HDR. So that's wider dynamic range, and it's all running the ISP function on the Xilinx Zinc 730. Okay, so if that's of interest, I encourage you to take a look. I've mentioned this a couple times, this near infrared plus. For those that are not aware, when in the daytime, as the sun goes down and your available outdoor light goes down, your visible light decreases faster, obviously because it gets darker, and therefore, however, the near IR photons that are out there actually are still there at that dusk and low light periods. So if you have a sensor that is more sensitive in that 850 and beyond, not only is it more sensitive for your LEDs, your near IR LEDs, but it's also more sensitive for the available near IR light out there. So one of the things that one of the technologies that we do at on Semi is try and improve that near IR sensitivity so that the sensor is able to pick up that. And so what you see here, once again, the overhead projector doesn't do quite justice, but you kind of get the flavor of it. You see this standard silicon is fairly dark, but if you use that near IR technology, you're able to get a 3x the sensitivity under low light conditions. Okay. Another trick or another technology that we've incorporated too is at On Semi we have our own in-house color filter arrays. So when we say color filter arrays, that's the micro lenses and the filters that we put on top of the image sensors to make it either a mono sensor or a quote color sensor. Most of the color sensors are around this Bayer pattern. We do offer also a larger variety of other color filter patterns. Sparse, you may be aware of that was patented by Kodak many years ago, but also there's a larger range of different color filter arrays that we are able to do since we have that capability in-house. And but one of those is this what we call RGB IR. And what you're seeing is we're deploying, this is your standard Bayer pattern, and then there's 2 variants, what we call a 2x2 kernel and the newer 4x4 IR kernel, and we're replacing some of these pixels with these IR pixels. And what you're able to do with that is, in simple terms, is you're collecting this IR data. You've still got the other data the IR data coming through the B's and the G's and the R's. And so you're getting all your color data out of there. You're able to subtract out the IR data through your image processor and then kind of recombine things throughout the array. And the end result allows you to do better color reproduction using that sensor. And the feature is, what you're seeing here is the 2 images show when it's done incorrectly here at the top, is you get a purple bush. Generally, bushes don't come in purple, but if you do the IR subtraction correctly, then you get actually a green bush, and you get better color fidelity. One of the other advantages of this technology is oftentimes in day, quote unquote, low light cameras, you have to incorporate a near IR cut filter that helps out with the fidelity, once again, the human fidelity of the camera. So you put the IR cut filter in there, cuts out all your near IR photons during the day, so you have a nice color image. But when it starts getting low light, you have to have a manual shutter that flips in and takes out the IR cut filter to get that near IR wavelengths, right? Those photons that I talked about earlier at dusk. And so that becomes this whole clicking on and off is not necessarily that adds complexity, it adds power and everything else. But if you think back to the wildlife camera situation, right? So you want the camera, like a wildlife camera, to be able to operate daytime and those low light applications, but you don't want some kind of clicking or noisy shutter moving in and out. Because you're going to spook the deer that you're trying to film, or whatever the animal is you're trying to film, and be able to track. So those types of, obviously for a doorbell cam, it's probably not that big of a deal, but for other applications, it can be very important. And that's where you might want to look at a solution like a solution with an RGB IR. Okay. Along with that, I talked about I wanted to throw up an example here of other linking of some of our customers. This is a LumiLED infrared LED evaluation kit that just bolts onto. This is our standard, what we call our Demo 3 evaluation kit, and I'll talk a little bit more about that. Okay, moving on, I kind of touched on this. Another technique when we're dealing with low light applications is, I mentioned earlier about the body camera using small pixels. One of the ways, and if you use a bigger pixel, you're often going to get a better image quality. And so that's essentially what this device is showing. What this slide is showing here is, this is an Aero 237. It has a fairly small pixel, but if you use a larger pixel, the Aero 221 with a 4.2 micron, you actually, versus the 3 micron here, this is a 3 micron and a 4.2, you actually, it represents, a 2x increase in the area. And so you improve that low light performance and here in this bottom image. So you can see, if I just told you, hey, which would you rather have? I think more than likely you'd pick this one if I didn't tell you it was 4.2 micron pixels. So, or any other details. So this is also a 1/2 inch sensor versus a 1/3 inch sensor. So those are some of the things I wanted to get folks thinking about when you're looking at some of these imaging sensors, because there is, to your point, there is quite a bit of difference and difference in performance, even though, as I think we have at least probably 10 or 20 different standard 2 megapixel sensors. Okay, let's move on a little bit to robots. As Pavan talked about, robots are increasingly widespread. I'm not going to spend a lot of time on the numbers, but you're seeing more and more use of automated systems and robots. In our homes and also in the workplaces. Though you may be familiar with, this is the little delivery robots. There's several companies doing that. You've got robots for customer service, etc. This is definitely a large area, and with more and more robots, this machine vision and becomes more important. Latency is a key thing. That's the time for the actual edge sensor or the edge camera to be able to process that data, apply intelligence to it, and then be able to act on that. Bandwidth obviously comes into play. Bandwidth of having all these sensors in your home. You got to increase the bandwidth of your routers, et cetera, to deal with that. And of course, privacy and being able to scale this depending on, for example, if you had delivery going from one delivery robot or one automated forklift. Think about that. There's a lot of talk on the industrial side of automated or manless or autonomous forklifts running around, and Amazon and through their Kiva systems and other companies as well are doing many hundreds of little robots running around factories. It's not just in automotive, more and more in warehousing, etc. So all these things come into play. Here gives an example of some of the typical block diagram for robots, master control, image sensors, radars, ultrasounds, etc. Like I said, if you've got, if this is of interest, definitely reach out to the onsemi team and we can deep dive into this further. Okay, I just want to kind of touch on also, really going back, building on that theme of the cloud and the IoT. Same thing in the machine vision world. It's all about these sensors and getting that good quality data, and then being able to build on that machine learning, and then how do you leverage that into improving your particular situation. So we're going to see more and more of that in the coming years, incorporating that. We talked about. Here's some more examples of robotics and the development of those. You're seeing more and more. I will talk about depth. Depth is another, being able to take an image sensor, using an image sensor and being able to incorporate and understand depth. How far is that robot from the wall or chair, etc., or from a person? So that becomes increasingly important as well. So when we talk about solution side of things and more the machine vision, we talked about a lot of this in the edge AI side. So I want to throw some sensor part numbers and sensor products up here, or solutions to get you more focused. We talked about this little ARX being a fairly low cost, low resolution, but has some a lot of power for the money and a lot of capability. Then you got the 2 megs are what we call kind of our edge AI, but you can use any one of these devices across these applications. So I don't want to limit you. I go back and evaluate some of these sensors. This XGS I haven't talked about. This is what we call this is part of our global shutter family. It's all built around a 3.2 micron pixel for kind of anything from commercial applications, consumer, all the way up to very high-end industrial machine vision applications, even the 45 meg, the 12 meg. There's also a 30 and a 20 in there, all used for inspecting flat panels, phones, and that sort of thing. But the exact same technology and pixel performance you can get in a 1.3 megapixel. That's could be as down as $30. So it just depends on, once again, take a look, depending on your application. I didn't talk, and then the Python family is a little larger pixel. They've got a little different, it's a little different architecture. And the key difference there is the Python has the ability to do some really high frame rates. So if you were to take this 1.3 megapixel sensor, shrink the ROI down, you can actually get that little part up to close to. I got customers running that at over 1,000 frames per second. So if you want to shrink it, and you might say, well, what's interesting? Well, that's interesting for a lot of motion analysis customers. So think of where you've got something, you want to track something through a scene. So like a golf ball simulator or a swing analysis, and you want to be able to see, you have a larger field of view, take an ROI, track the golf ball club as it coming into the field of view, and then track the contact when it hits the golf ball, and then be able to track at a higher frame rate where the field of view may be running at 30 frames, but that little golf ball tracking that club head and the golf ball contact may be done at, say, 500 frames per second. So if you've got an application like that, or motion analysis where you're doing the body movement, trying to track that sort of thing at a high frame rate, we got one target or multiple targets at really high frame rates, that might be a family for a better solution for you. Okay, I mentioned earlier, touched on this global shutter. Global shutter refers to the architecture of the image sensor, and in general terms, you've got two prevailing architectures: rolling shutter devices and global shutter. Most of your rolling shutter devices now have that, what we call backside illuminated technology, and allows you to do that with the rolling shutter. It's much easier to do. Backside illuminated improves that sensitivity of the sensor to convert those photons into usable electrons. Global shutter today, mostly 90% of them, 95% of them are going to be front side illuminated. So you may require a little bit more light or a little bit more sensitivity. But the key difference, as you see here on the fan, is the ability to deal with motion. So if you've got barcode scanners are all global shutter. Industrial inspection systems are all global shutter, because you're dealing with either something, the target is moving down a manufacturing line and you want to take a quick snapshot of it, like a bottle or whatever the thing is, an apple or tire treads coming over it. You're trying to measure that. You'll need a global shutter device more often than not. And then for those rolling shutter devices, most of your security cameras are actually rolling shutter devices, because your targets are not moving that fast. Humans are not moving that fast. But if you're in a car, more and more cars are using global shutter, because the side view cameras, the cars are moving at 60 miles an hour. So if you want to get a clear, usable image that you want to apply AI to, that machine is going to need a global shutter image. So once again, if your target or the camera itself is moving, you want to make sure you take that into consideration. Okay, and then I mentioned the XGS family. I'm not going to spend a lot of time here. This entire family is all built around the same pixel, and it's scalable from XGS products are available in 1.3 all the way up to 45 megapixels, all built around the same global shutter. And so if you're in some of these applications, 3D depth mapping, once again, it may not be a motion application, but you see the user here taking a camera, trying to scan a room. That's motion. You want to have usable, good data here, as well as in this. This is also showing here global shutter for movement and tracking drivers as well, and in-cabin awareness or other similar applications. So. Okay, I'm not going to show that this is, once again, a similar touching on it. There is some other features here. You want to talk about global shutter features. It's the clarity. What you see here is, you see on this image on the left, is this little clouding. You kind of see back through the fan, and a good global shutter device, you're going to see the full business card. So that's another key feature. Some companies call global shutter efficiency PLS. So that would be another way it's that same feature is specified. Sorry. I'm not going to spend too much time. This is just a quick overview of some of the solutions that are available on, these are all, these two are 1/3 inch format. This is a 1/4 inch. Some of our global shutter sensors for commercial and consumer applications. This I want to also share with you just a quick announcement. I mentioned earlier we do have, this is our Demo 3 DevWare software kit, and so typically what we tried to do in this kit is you have one baseboard, and then you have each of the different sensors has a different headboard, or most of the different sensors have a headboard. So once you get the baseboard, you just need to plug on the different headboard for each individual sensor, and then the software is really powerful. I encourage if you are looking at developing your own image sensor or looking at image sensors, it's a great, easy way to evaluate different sensor solutions and then put that kit into your real life application. So a couple more slides. I mentioned earlier the modules and the way I mentioned the modules, the idea behind the modules from a developer standpoint, right? Here's just a diagram of modules. You can link it up to a Demo 3 interface board, and then that connects to that same Demo 3 board that you saw on the previous slide. And then we were also working on, you'll see the start of this also next door is a link to, you can take that same module, put a interface board, same connector here, and then it goes into, say, a partner reference design that you see, that you saw next door on the NVIDIA Jetson board set. And the idea behind it is you can do all your development work here, and then that exact same module goes into your finished product. And one of the things we worked strongly with our module partners and our distribution partners on with modules is to help ensure ensurety of supply chain and the design chains. That's one of the big drawbacks to modules is the module manufacturers will make 100 million units for one particular customer, and then they'll try to sell the leftovers to whoever there is, and then you go off and design that module in, whether it's from, and then you find out 6 months later they've changed the field of view, they've changed the spec, the connector. You can't get support because you're not buying 100 million units, that sort of thing. So with this IAS program from On Semiconductor, we're hoping, and with partnering with our distribution partners, that it eliminates a lot of those risks of supply chain, design, and actual product changes. And we work with them so that these module designs are not going to change for at least a minimum of 4 years. So that should hopefully, get you started, make your lives easier on that side of things. Also, I just want to throw up a couple examples. I talked more about them already. The SnapCam example that's next door. This is also the Xilinx solution here, the AP1302 with their Aero 430 module. And then there's also another example there of a battery-powered camera, and you'll see one as well next door with the SnapCam. Okay, so key takeaways, last slide, is there's a huge set of opportunities in IoT, Internet of Things, all sorts of different use cases, needing and looking for image sensor solutions. Make sure you do your homework or rely on the onsemi team or our distribution partners. I know at least 2 of the distribution partners here have their each of the distributors have their own imaging FAE specialists that just do imaging sensors. So I encourage you to leverage those resources. I know that John Stye is here from Future and Griffin Peterson from Avnet. So I encourage you to reach out to both those 2 gentlemen to talk about your particular needs or interests. And then to look through, do your evaluation on the sensor performance, because we talked about pixel size. We talked a lot about optical format and HDR and NRR+. Those are all things and key parameters that you want to take into consideration on the design evaluation side of things. Test it out in your application before you get down this road, and then you go to launch your product and then you find out that, oh, I can't see anybody in the shadows. So definitely want to do your homework there, and then leverage our partners. We're at onsemi, we're trying to increasingly move beyond just throwing a sensor out to yourselves and say, here you go make it work, but also being able to leverage those partners and creating an ecosystem and modules and reference designs to hopefully make your lives and your design lives much easier.